All right, this is going to be a supplemental lecture covering section 7 and section 8 of chapter 1. Remember, we have to go over this because we missed a couple of days, one for the weather day and of course for the holiday. So chapter 1, section 7 tells about inequalities. And I'm just going to go over the type of problems you're going to see in the homework attached to the Blackboard class that I created. So the first type of problem will be a linear inequality. So if we're given the inequality negative 2x plus 7 is less than negative 5. Just as a quick reminder, this is less than, greater than, and of course if they have the lines up under them, they'll be the or equal to. So this is less than or equal to, greater than. All right. So the first type of example, linear inequality. And with these inequalities, we're going to solve them just like we would an equation. All right. Only difference is instead of an equal sign, we're going to have an inequality. So first thing I would do here, subtract 7 from both sides. That's going to leave me with a negative 2x on the left-hand side of my inequality. Then positive 7 and then negative 7 is going to cancel out. Strictly less than. Negative 5 minus 7 will give me negative 12. And to get the x by itself, we need to divide both sides by negative 2. We want to remember that if we divide by a negative, as we've done in this case, the inequality would flip. So negative 12 divided by negative 2 is going to leave me with a positive 6. So my answer is x is greater than 6. Now in set notation, our answer is all the values greater than positive 6 or the set containing x. That straight up and down line means such that x is greater than 6. I remember we're doing this work on the computer, so they may ask you to present it in a set notation. But more often than not, it's going to be an interval notation. So in interval notation, the reason I personally like to keep my x on my variable on the left is I can think of the inequality like an arrow pointing in the direction in which I need to shade. So on the number line, that positive 6. I'm on the number line, if it's strictly greater than, strictly less than, we have an open circle. And all the values greater than positive 6 to the right. All right. So strictly less than, strictly greater than, get parentheses, like I put around the words. Well, greater than or equal to and less than or equal to, we get brackets. So this answer in notation, lowest value first, open parentheses to show that we're excluding positive 6 in my answer to positive infinity. And infinities always are encompassed in parentheses. Right. Next type of problem that we're going to see. Still dealing with linear inequalities. This time we're given 3 minus 4x is greater than or equal to 2x plus 8. Right, so like I said before, I like to have my x's on the left. This way I can think of the inequality as an arrowhead showing which way to shade. So I'm going to bring my x's to the left by subtracting 2x from both sides. Bottom of like terms, of course. And I'm going to go ahead and move that positive 3 to the other side of the equation by subtracting 3 from both sides. So the 3's will cancel, my 2's will cancel. Negative 4x minus 2x will give me a negative 6x, greater than or equal to 8 minus 3 will leave me with a positive 5. Now we need to divide both sides by negative 6 to get the x by itself. Like we said before, if we divide by a negative, the inequality will flip. So what was greater than or equal to becomes less than or equal to. And x is less than or equal to positive 5 divided by negative 6, leaves me with a negative 5, 6. So on the number line, we have a negative 5, 6. This time we'll have a closed circle to show that negative 5, 6 is a part of my solution set. We know this because of the or equal to. We're going to shade to the left. Remember that x on the left-hand side. This is an arrowhead showing which way to shade. So in interval notation, this goes to negative infinity. You want to write the less The least value first, so it'll be from open parentheses, negative infinity to negative 5, 6, close bracket to show that negative 5, 6 is a part of my solution set. Next type of problem we'll have is compound inequality. I refer to these problems as and problems. All right, so another way of thinking of this is a three-sided inequality. So an example of this, inequality 1 less than or equal to 6x minus 8, which is less than or equal to positive 4. All right, so this and our compound inequality, what I like to do is refer it back to regular inequality. We'll solve this like an equation, get an x by itself. The only difference is whatever we do to two sides, in this case, we would do it all three. So here, to get the x by itself, first thing I would do is add 8 to both sides. Because it's an and problem, our compound inequality, we're going to have to add 8 to all three sides. So I'm left with 6x in the middle. I'm going to bring down my inequalities exactly as they are. 4 plus 8 will give me 12. 1 plus 8 will give me 9. Still trying to get the x by itself. And divide all three sides by positive 6. Now note this time, because we divided by positive, none of the inequalities change. So 9, 6 reduces down to 3 halves. We're left with just the x in the middle. Still less than or equal to 12 divided by 6 is positive 2. All right, now because the reason I call this an and problem, because x is greater than or equal to 3 halves and less than or equal to 2. So the solution set is in between two numbers, those values being 3 halves and 2. Every value in between 3 halves and 2 is going to be shaded. And because it has the or equal to symbols, we're going to include those values in my solution set. On the number line, we'll have closed circles. So I always like to refer to people to know that and problems are always in between two values. In interval notation, it will be open bracket, 3 halves, comma 2, close bracket. Next type of problem we're going to have in this section, quadratic inequalities. I apologize if I'm moving fast. Just take advantage of the fact this is a video, so you can pause it as much as you like. All right. So the first step is solving quadratic inequalities. Is to set it or solve it as an equation. And the reason we want to solve this as an equation is because this is how we're going to get our linchpin numbers that are going to divide up the number line. Remember, if it's a quadratic, typically we get two solutions. Those solutions are going to divide the number line up into three segments, and we're going to figure out which segment is a part of our solution set. And then 2, we're going to test the values for a true statement. All right, so once we divide it up into those intervals, I pick a number in those intervals and test it. Now, typically, the intervals stagger. So once we find a true statement, that's going to be our solution set. But if we test a number from that interval and it is not true, or it gives us a false statement, then the outsides are technically the interval notation. Now, you can always take a value and test each interval, but for the sake of time, I'm just going to use the fact that I know that they stagger and just test them as so. This way, we only have to really test one number from the interval. I can lean on the fact that 1s, 0s, and 10s are easy to add, subtract, multiply, and divide. So our first example would be the quadratic x squared minus 2x minus 15 is less than or equal to 0. So our first step is to set it up like it's an equation. We have x squared minus 2x minus 15 is equal to 0. And here we have a quadratic with a leading coefficient of 1. We can jump right into our factor. We're looking for two numbers we can multiply to give me negative 15 that I can combine, add or subtract to get negative 2. Those values are 3 and 5. And in order for us to get a negative 15, one of them must be negative. In order for us to get a negative 2, the 5 must be negative, which in turn tells me my 3 is positive. Remember, my solutions are the opposite of what we see in our factors. So my solutions will be -3 and +5. These are going to be my linchpin numbers that are going to divide up my number line into 3 segments. Keep in mind, lesser value goes first. So we got 3 and we have 5. Remember, these values will make the quadratic equal to 0. The original question is less than or equal to 0. So that lets me know that both 3 and 5 are a part of my solution set, because these are the values that make it equal to 0, and this inequality has an or equal to sign attached to it. Now, an easy number to test, or the easiest number to test, would be 0. Or we'll test that interval of the values in between 3 and 5. So we're just going to take that 0, plug it into our original question. If it gives us a true statement, we know all the values in between 3 and 5 are part of my solution set, which in turn tells me that the values on the outside are not. Now, like I said, for the sake of time, I'm not going to test those other 2 intervals, because if it's true, then we know it's right here. These are not. And if it's false, then it's going to be on the outsides and the inside is not. So we're going to have x squared, or in this case, 0 squared, minus 2 times 0, minus 15, trying to see if this is less than or equal to 0. So that's going to give me 0 minus 15. Of course, that's -15. It's less than or equal to 0. This is a true statement. That lets me know that all the values in between 3 and 5 will work. So in interval notation, open bracket to show that 3 is a part of my solution set, comma 5, close bracket. This lets me know that every value in between 3 and 5, including both 3 and 5 themselves, is a part of my solution set. Another example, quadratic inequality. If we're given the quadratic x squared plus 5x minus 24 is greater than or equal to 0. I'm going to set it up like it's an equation. X squared plus 5x minus 24 is equal to 0. Once again, we have a quadratic with a leading coefficient of 1, or a trinomial with a leading coefficient of 1. So we can jump straight into our factor. Looking for 2 numbers we can multiply to give you -24 that we can combine or add or subtract to get 5. Those values are 8 and 3. And in order for us to get a -24, 1 must be negative, either the 8 or the 3. In order for us to get a +5, the 3 must be negative, which in turn tells me my 8 must be positive. Take the opposite of what we see in our factors to get our solutions. -8, +3. This is going to be my linchpin numbers, which is going to divide the number line up into 3 segments. So we're going to have values less than -8, values in between -8 and 3, and values greater than 3. Just like before, you test 0. Also keep in mind, these values, both -8 and 3, will make the inequality, the quadratic equal to 0. And because it says greater than or equal to 0, we know both -8 and +3 are a part of my solution set. We're going to take that 0, run it through our quadratic. So we'll have 0 squared plus 5 times 0 minus 24, trying to see if that's greater than or equal to 0. We know 0 squared gives 0, plus 5 times 0 is 0, minus 24, which is -24. Trying to see if that's greater than or equal to 0. This one is a false statement. Like I said before, it's typically staggered. So if we know all the values in between -8 and 3 will not work, that means the values on the outsides will, or values less than -8 and values greater than +3 will be my solution set. So in interval notation, we have -infinity to -8, close bracket, union, open bracket, 3 to infinity, close parentheses. Now, if we want it, we could take, let's say, -10, plug it in this quadratic, and you'll see that we end up with a positive answer, which of course is greater than or equal to 0, which gives us a true statement. But once again, for the sake of time, remember, your test will be multiple choice, and it will be time. It may help you just to understand they are typically staggered. All right. Last type of inequalities that we're going to see in this section are rational inequalities. Remember, it's just a fancy way of saying fractions. First step for these rational inequalities, we're going to take the numerator and the denominators. And set them equal to 0. This is how we're going to find our linchpin numbers for rational inequalities. Then we're going to graph and test the points. So it's just like the quadratic inequalities, except that when we get our linchpin numbers, we won't factor this time. So we take the numerator, denominator, set them equal to 0. And keep in mind that we can never divide by 0 with our fractions, and we're looking for true statements. So our first example in this section of this type of problem, we're given the inequality 4x minus 18 over x minus 3 is less than or equal to 0. So like it says, we're going to take the numerator, 4x minus 18, set that equal to 0. And our denominator, x minus 3, set that equal to 0. Now, if we solve this, 4x minus 18, we'll end up with a solution, x is equal to 18/4, or it reduces down to 9/2. That's going to be one of my linchpin numbers. And of course, the solution for x minus 3 is equal to 0 is x is equal to positive 3. That's going to be my other linchpin number. All right, so we're going to find those values in the number line. We're going to put our 3 first, that's a value. Remember, 9/2 is really 4 1/2. So a good number to test in between would be 4. Now, this says less than or equal to 0. The only way we're going to get 0 dealing with a fraction is if my numerator is 0 and we divide by something other than 0. Remember, if we divide by 0, we don't get a solution, or it's not defined. So we know 9/2 is what makes the numerator 4x minus 18 equal to 0. So 9/2 is going to be a part of my solution set. So we're going to put a closed circle here. Where if x equals 3, we end up with the denominator of 0, 3 minus 3. We cannot divide by 0, so we have to exclude 3 in my solution set. Now we're going to use this 4 to test all the values in between 3 and 9/2, plugging into our original problem to see if it gives us a true statement. But it's going to be 4 times 4 minus 18 divided by 4 minus 3, trying to see if it is less than or equal to 0. That's going to give me a -2 over 1, which is -2. Trying to see if that's less than or equal to 0. This is obviously a true statement. All negative values are less than 0. So all the values in between in between 3 and 9/2 are part of my solution set. And remember, it staggers. So this is a true statement, which means this goes false, true, false. We can always test a value less than 3. Good one would be 0. Or a value greater than 9/2. Another good one would be like something like positive 10. All right. So in interval notation, there will be open parentheses to show that we're excluding the value 3, comma, 9/2, close bracket to show that we are including the value 9/2. Another example, same type, rational equation, rational inequalities. We have 6x minus 19 divided by 2x minus 3. And this one's strictly greater than 0. All right, so just like we did before, we're going to take our numerator, set it equal to 0. In this case, 6x minus 19 is equal to 0. And my denominator, 2x minus 3, setting that equal to 0. And this time, because it's strictly greater than 0, we can't get 0. Or if any value to make it equal to 0, it's not going to be a part of our solution set. So for the first one, 6x minus 19, if we solve that, that would give me 19 over 6 as my solution. And for 2x minus 3, that will give me a solution of positive 3/2. So these are my linchpin numbers that we're going to divide up our number line with. So we're going to pick a value. For me, I'd probably pick a number in between 3 halves and 19 halves. I actually got a few candidates here because we don't have zeros, ones, or tens. So I'm just going to use 3. And we can actually go ahead and put open circles on both 3 halves and 19 halves. Remember, 19 halves, when my numerator equal to 0, 0 is not greater than 0 is equal to. This does not have the or equal to symbol, so we have to exclude it. And obviously, I'm sorry, did I say 19? Yeah, 19.6 will make the numerator equal to 0. Can't have that because it doesn't have the or equal to. 3 halves makes the denominator equal to 0. We can never divide by 0. So both of those values will be excluded in my solution set. I'm going to take my 3, the test the values in between, plug it into my original inequality to see if it gives me a true statement. So I have 6 times 3 minus 19 divided by 2 times 3 minus 3. See if that gives me something greater than 0. We actually end up with negative 1/3, which is a false statement. Obviously, negative 1/3 is not greater than 0. So none of these values in between 3 halves and 19.6 will work, which in turn tells me the values on the outside will. Now, just to be sure, you can pick a value less than 3 halves, or each one will be 0. This will give me negative 19 over negative 3, which is a positive value. Obviously, positive values are greater than 0. But once again, they're typically staggered. So if you want to save some time or you're running out of time on the test, just remember that they're staggered, and 9 times out of 10, you'll get it right. And interval notation will be open parentheses, negative infinity, 3 halves, close parentheses to show that we're excluding 3 halves as our answer, or it's not in my solution set. Open parentheses, 19.6 to infinity, close parentheses. Those are all the types of problems we're going to see in 1.7. We're going to go over the types of problems we're going to see in 1.8 are absolute value inequalities. So solving an absolute value inequality, our first step, isolate the absolute value if we're dealing with equations. And we're dealing with absolute value equations. I have 2 answers, which is a little counterintuitive. Remember, absolute value forces everything to be positive, which means that if we're taking the absolute value of a negative number or a positive number, our answer ends up being positive. This is where we get those 2 answers. I'll show you what I mean in this first example. Here we have the absolute value of 9 minus 4x is equal to 7. So the way that we get rid of those absolute value bars on the problem is to account for both the positive and the negative of the answer given. So here, to drop out the absolute values, we have to set up 2 equations. The first one being 9 minus 4x is equal to positive 7, accounting for the positive. And then 9 minus 4x is equal to negative 7, accounting for the negative. After that, we're just solving them like we would any other problem. First step, subtract 9 from both sides. That's going to give me negative 4x is equal to 7 minus 9. Give me a negative 2. Here, negative 4x is equal to negative 7 minus 9, negative 16. And to get the x by itself, divide. So that's going to give me x is equal to negative 2 over negative 4. It reduces down to a positive 1/2. And negative 16 divided by negative 4, using with a positive 4. So x equals 4 would give me a negative 7 for 9 minus 4x, and the absolute value of negative 7 is 7. And if x equals 1/2, that gives me a positive 7. And obviously the absolute value of positive 7 is 7. So this is how we get our 2 separate answers. Another type of problem just like that. So now we have the absolute value of 3x plus 2 is equal to the absolute value of x minus 5. Now remember, absolute value forces everything to be positive. So this can be a true statement, or this is a true statement. Positive equals a positive. But we still need to account for the positive and the negative. So to drop off the absolute values, first we're going to write the equation 3x plus 2 is equal to x minus 5, accounting for the positive. And 3x plus 2 is equal to negative x plus 5, accounting for its exact opposite. After that, we're just solving here. I'll subtract x because I like to have my x on the left. Also, we'll subtract 2. So the 3 minus x will give me 2x is equal to negative 5 minus 2, which is negative 7. Divide both sides by 2, and x is equal to negative 7 halves. That's my first solution. We can solve this one doing the same process, just putting my x's on the left. This time I'm going to have to add x to both sides. Still subtracting 2 from both sides. 3x plus x gives me 4x is equal to 5 minus 2, 3. Divide both sides by 4, and then with x is equal to 3/4. Next type of problem we have to deal with, absolute value inequalities. Yep. Isolate the absolute value, just like we did in previous problems. Second step, you're going to have two inequalities that will account for the absolute value, accounting for both the positive and the negative. And don't forget that if we divide by a negative, flip sign. And then lastly, once we have those two inequalities accounting for both the positive and the negative of the absolute value inequality, we're going to solve. Now, what I like to tell people is remember this saying, less than and. This is how we're going to get rid of the absolute value symbols and a less than inequality. Greater than or. And I always focus on the or because I think, the way I think of it is or starts with O. And on the number line, where the absolute value inequalities, they have greater than in them. We have to count for the positive and the negative. Here, we don't know what those values are, so we'll just call them C. And our answers are going to be on the outside of those values. Keeping in mind that if it's greater than, then it's an open circle on those values. If it was greater than or equal to, closed circle to those values. This is how we're going to remember this number line will help you set up those equivalent statements on how to get rid of those absolute value inequalities. Absolute value bars in the inequality. I'll show you what I mean. First example, the absolute value of 4x minus 6 is less than 10. The way I think of it, I read the problem, the absolute value of 4x minus 10, excuse me, the absolute value of 4x minus 6 is less than 10. I said less than, so it's an and problem. This is going to be a compound inequality. So to get rid of my absolute value bars, I'm going to account for the negative. I'm going to negative 10. Bring down that same less than, because whatever x is going to be in between those opposites here, 10 and negative 10. I'm writing the equivalent statement so I can drop off my absolute value bars. Still less than 10. Now we can solve the compound inequality like we did previously by first adding 6 to all three sides. It's going to leave me with 4x. Bring down my inequalities. 10 plus 6, 16. Negative 10 plus 6, negative 4. Last step is divide by positive 4. It's going to leave me just with x, which is exactly what I want. And because I divided by a positive, my sign stayed the same. Negative 4 divided by positive 4 leaves me with a negative 1. 16 divided by positive 4 leaves me with a positive 4. So this is my answer. X is in between negative 1 and 4. So on the number line, We have -1, 4, open circles on both, and shading in between the two. In interval notation, open parentheses, -1, comma, 4, close parentheses. So if it's a less than problem and or three-sided inequality. Another example, the absolute value, 2x plus 1, is greater than 7. Right. So remember, if we read the problem and say less than, three-sided or compound inequality and problem. Or if it's greater than, like here, that would be an or problem. Or problem should be outside of those opposite values. Keep in mind, anytime we use the absolute value, we have to count both the positive and the negative answer. So the way that I use this number line, my solution, x is going to be less than the smaller value, greater than the biggest value. Until that makes sense, this is what I tell you to do. Drop off the absolute value bars and write exactly what you see. So here, this would be 2x plus 1 greater than 7. Or write the same thing, except now, after 2x plus 1, we're going to flip the inequality and account for the negative. So x is greater than the biggest value, less than the smaller value. That's how we're going to shade on the outsides. After that, we're just solving it. -1, -1, -1. It's going to give me 2x is greater than 7 minus 1 is 6, or 2x is less than -7 minus 1 is -8. Still trying to get the x by itself, so we're just going to divide by 2. It's going to give x is greater than 6 divided by 2 is 3, or divided by 2, it's going to be x is less than -8 divided by 2, -4. All right, so on the number line, that's a value first, so -4, +3. Open circles on both because it's strictly greater than, strictly less than. We're going to shade on the outsides because it's an or problem. Just remember that or starts with O, so we're going to shade on the outsides. So our interval notation, -infinity, comma, -4, close parentheses, union, open parentheses, 3, comma, infinity, close parentheses. Last type of absolute value inequality that you may see, when you actually have the absolute value. So here, I'm going to have the absolute value for 2 minus 7x minus 1 greater than 4. First thing you do, move anything that's outside of the absolute value bars, it's on the same side of the inequality to the other side. So to move this -1, I have 1 on both sides. Absolute value of 2 minus 7x is greater than 5. As a greater than symbol, so this is an or problem, we know our answer is going to be on the outside of 2 values, accounting for both the +5 and the -5. Notice that we don't account for the positive and the negative until we get the absolute value by itself. So remember, 4 problems on the outside of those positive and negative. So it needs to be less than the smallest value, greater than the biggest value. So write it exactly as you see it without the absolute value bars. Sorry about that. 2 minus 7x greater than 5, bigger than the biggest value, or 2 minus 7x less than -5, smaller than the smallest value. All right, exactly as we see it without the absolute value bars. Change the inequality, flip the sign. After that, we're just solving, keeping in mind that if we divide by a negative, sign flips. So here, subtract 2 from both sides, that's -7x greater than 5 minus 2, +3. And then we're dividing by -7. So what was greater than is now less than. left with just x. And it's going to give me a positive, oh, excuse me, a negative 3/7. Is a part of my solution set. Or we're just going to solve this in the same fashion. Subtract 2, subtract 2. Negative 7x is less than negative 7. Divide by negative 7. The inequality should flip. With x is greater than positive 1. So on the number line, we have negative 3/7, positive 1, open circles on both, and it's an OR problem. So we're going to shade on the outside. So in interval notation, we open parentheses, negative infinity, comma, negative 3/7, close parentheses, union, open parentheses, 1, comma, infinity, close parentheses. You want to make sure to attach the homework to the sections in the Blackboard class. Be sure that you try it. Remember, class next week, the first day of class next week is for the review. And depending on which class you are on mine, either Wednesday or Thursday is the day of that test. All right. Good luck studying.